All right, let me start in a simple way. When people hear about modern physics, they often imagine something distant, abstract, and cold. Equations flying around like mosquitoes on a summer night. But physics is not really about equations. Equations are just the language we use after we already understand something. Physics is about noticing how the world behaves and asking again and again why it behaves that way. So let me begin with a question that sounds childish but is actually very deep. Why do things have weight? Or if you prefer a more careful word, why do things have mass? Why is it hard to push a refrigerator but easy to push a pencil? Why does light move so easily while you and I do not? At first glance, the answer seems obvious. The refrigerator is heavy, the pencil is light. But that is not an explanation. That is just a restatement of the problem using different words. Physics is not satisfied with that. Physics wants to know what is going on underneath. For a long time, people thought mass was just a basic property. An object simply had it, the way it has a color or a shape. End of story. But the deeper we looked, the more uncomfortable that answer became, especially when we started to understand nature at its smallest scales. When we zoom in far enough, the world stops looking like solid stuff and starts looking like activity. Little points, fields, interactions, exchanges. In that picture, mass becomes a problem, not a given. Now let me tell you something that sounds strange if you have not heard it before. Empty space is not empty. If you take all the air out of a box and then all the atoms and then all the radiation, you do not get nothing. You get a very busy place. Space itself has property. It can stretch, it can vibrate, it can store energy. In modern physics, space is filled with things we call fields. A field is not a thing you can hold. It is more like a condition. Temperature is a field. At every point in a room, the temperature has a value. Wind is a field. At every point in the sky, the air has a speed and a direction. You do not ask where the wind particle is. You ask what the wind is doing here. In the same way, physics describes nature using fields that exist everywhere, even where there are no particles. There is an electric field, a magnetic field, and many others that are less familiar but just as real. Particles, in this picture, are not little solid beads. They are small, localized vibrations of fields, like ripples on the surface of a lake. This idea already pushes us toward calculus, though we do not need to write any formulas. Calculus is about change and continuity. A field is something that has a value everywhere, smoothly changing from point to point. Once you accept that the world is made of fields, calculus becomes almost unavoidable, because you are always asking how something changes as you move through space or time. Now light gives us a beautiful clue. Light has energy. It can push things, it can heat things, it can even carry momentum. But it has no mass. No matter how energetic a beam of light is, it always moves at the same speed. You cannot slow it down by loading it with extra energy. That is very strange if you think mass is just a measure of how much stuff there is. Electrons, on the other hand, do have mass. They resist being accelerated. If you push them, they respond sluggishly compared to light. Why the difference? Both light and electrons are described by fields. Both are excitations of something spread throughout space. So why does one behave as if it is heavy and the other as if it is weightless? This question haunted physicists in the 20th century. The equations that beautifully describe the forces of nature seemed to prefer particles with no mass at all. When mass was added by hand, the equations lost their elegance and, worse, their consistency. Nature, however, clearly does not agree with equations that only allow massless particles. We exist, tables exist. Something had to give. To understand what finally worked, we need to talk about symmetry. Symmetry is one of those words that sounds artistic but turns out to be deeply practical. A circle is symmetric because it looks the same no matter how you rotate it. The laws of physics are symmetric because they look the same no matter where you are or when you perform an experiment. Symmetry is powerful because it restricts what is allowed. If you demand that a system behave the same under certain changes, many possibilities disappear. This is both a blessing and a curse. The blessing is clarity. The curse is that sometimes reality does not fit neatly into the most symmetric picture. Here is a simple example. Imagine a pencil balanced perfectly on its tip. The situation is symmetric in all directions. But the pencil never stays that way. It falls. And when it falls, it chooses one direction, breaking the symmetry. The laws allowed all directions equally, but the outcome didn't. This idea, called symmetry breaking, turns out to be essential. The laws can be symmetric even if the state of the system is not. Once you see that, a door opens. Think of a landscape with hills and valleys. A ball placed exactly on top of a hill is in a symmetric position. Every direction is the same, but the slightest disturbance sends it rolling down into one valley. Once there, the symmetry is gone, even though the landscape itself was symmetric all along. In physics, fields also have landscape. They have energy, and that energy depends on the value of the field. Nature prefers low energy, the same way a ball prefers the bottom of a valley. The lowest energy state of a field is called its vacuum state. This word is misleading because it does not mean nothing. It means the calmest configuration. Space itself is soaked in it, the way air fills a room. If that sounds odd, think of temperature again. Absolute zero is a special case. Most of the time, the lowest temperature available is not zero. The room settles at some naso temperature. That temperature is not caused by a particular object. It is just how the room is. Now imagine moving through such a space. Some disturbances pass through easily, barely noticing the background. Others interact strongly with it and struggle. That struggle shows up as inertia. A favorite way to picture this is to imagine a crowded room. The room is filled with people standing around. A person nobody recognizes can walk straight across without much trouble. But a famous person attracts attention. People cluster around, slow them down, make it harder to move. From a distance, it looks as if the famous person has more mass. The important thing here is that nothing is being added to the person. The difference comes from interaction with the environment. In physics, mass can arise the same way. It is not something stored inside a particle like coins in a pocket. It is something that emerges from how the particle interacts with a field that is already there. This idea solves the old problem elegantly. The equations can remain symmetric. The fields can behave nice, and yet particles can end up with mass, because the vacuum itself is not empty, not zero, not trivial. Advanced calculus sneaks in again here, quietly. When we talk about energy landscapes and lowest energy states, we are really talking about finding minima of function. Calculus teaches us how systems settle where change stops, where slopes vanish. Nature does the same thing without writing anything down. So space is filled with a field in a settled state. Certain particles interact with it, and that interaction makes them behave as if they are heavy. Others do not interact and remain light-like, racing along at nature's speed limit. Now, if a field fills all of space, it can also vibrate. Just as the surface of a lake can ripple even when it is otherwise calm, a field can have small disturbances around its settled value. Those disturbances are what we call particles. This is a general rule in modern physics. Every particle you hear about is a vibration of a field, no exceptions. The electron is a vibration, light is a vibration, and the field we have been talking about is no different. Its vibration is just another particle, one that appears only when you put enough energy into the system. Most of the time, the field just sits there quietly, doing its job, giving mass to some particles and ignoring others. It is tempting to treat that particle as something mystical, something fundamental in a religious sense. That temptation should be resisted. Physics is not about holy objects. It is about mechanisms. This particle is interesting not because it is divine, but because it confirms that our picture of fields, symmetry and interaction is basically right. But before getting ahead of ourselves, it is important to remember something. Understanding does not mean certain. Every answer opens new questions. Why does the field have the shape it has? Why does it settle at the value it does? Why do different particles interact with it differently? Physics, at its best, does not hide these questions. It puts them on display. What we have learned so far is already remarkable. Mass, which once seemed like a primitive property, turns out to be a consequence, a result of interaction, a kind of resistance caused by moving through a structured vacuum. This way of thinking changes how you look at the world. When you push a table and feel it push back, you are not just dealing with stuff. You are dealing with fields, symmetries and energy landscapes, all working together in a quiet, consistent way. In the next step of the story, one asks how we know any of this is true. How can you test the behavior of a field that fills all of space. How do you detect a vibration that exists only for a fraction of a second and leaves no trace? You can see. Those questions lead to remarkable machines, clever statistics, and a deep respect for uncertainty. But before we go there, it is worth pausing and appreciating how far simple questions can take you. Why is it hard to push a refrigerator? Because space itself is not empty, and moving through it is not always free. That is not the end of the story, but it is the beginning. Now let us continue from where we left off. Because once you accept that space itself is not empty, curiosity naturally pushes you forward. If there is a field everywhere, quietly sitting in its calmest state, and if some particles gain their mass by interacting with it, then the next question is unavoidable. How do we know this field is really there? Physics does not accept ideas just because they are elegant. Nature gets the final vote. The difficulty is obvious. You cannot scoop up a bucket of empty space and pour it on a scale. You cannot point to a spot and say, there is the field. Fields are detected only by what they do, never by what they are. This is not a weakness of physics. It is one of its great lessons. We never observe things directly. We observe interactions. Think about wind again. You do not see wind itself. You see leaves moving, flags waving, clouds drifting. From those effects, you infer that something is happening in the air. In the same way, the field we are talking about announces its presence through consequences. One of those consequences is mass, but mass alone is not enough to prove that a specific field exists. There could have been many other explanations. Physics is conservative in that sense. It keeps asking, what else would this imply? And then it looks for those implications. Now remember what I said earlier. Fields can vibrate, and every vibration of a field shows up as a particle. This is not poetry, it is a precise statement. A calm lake has a surf. A tossed stone makes ripples. Those ripples are not separate objects. They are patterns of motion of the water. Yet they behave as if they are things that move, spread, and interact. In exactly the same way, if space is filled with a field in a settled state, then small disturbances of that field must exist. They are unavoidable. Once you accept the field, you accept the possibility of its vibration. And that vibration has a definite energy, a definite behavior, and a definite set of rules. So the existence of the field predicts the existence of a particle, not because anyone wanted it, but because mathematics and logic leave no alternative. If the field is real, its vibration must be real too. This particle is unusual though. Most particles you know about, like electrons or photons, exist freely. They travel long distances. They form beams. They leave tracks. This one does not. It is heavy, unstable, and short-lived. It appears only when you concentrate a great deal of energy in a very small region of space. Why is that? Again, the answer lies in interaction. The vibration corresponds to moving the field away from its calm value. That costs energy. The steeper the energy landscape around the calm point, the more energy you need to make the field wiggle. In everyday language, that shows up as a heavy particle. Here calculus plays a silent but essential role. When physicists talk about the curvature of the energy landscape, they are really talking about second derivatives. Steep valleys resist displacement. Gentle valleys allow easy motion. You do not need to calculate anything to feel this idea. Try stretching a stiff spring and then a loose one. The stiffness tells you how strongly the system resists change. The field we are discussing sits in a very stiff valley. That is why its vibration is heavy and hard to produce. Most of the time, the universe does not bother. Only under extreme conditions does the vibration briefly appear, like a ripple caused by a massive stone dropped into a calm lake. So how do you drop such a stone? You build machines that collide particles at enormous energy. Not because physicists enjoy excess, but because there is no other way. To disturb the field significantly, you must concentrate energy. Energy and mass, as you know, are deeply related. When two particles collide at high speed, their energy can briefly reorganize into other forms. This is not magic, it is bookkeeping. Nature keeps track of energy carefully, but it allows it to change form. A moving particle can turn into a heavier one for a moment, provided the energy is available. These collisions do not create the field. The field was already there. They only shake it hard enough to make its vibration visible. Now detecting that vibration is another challenge. The particle does not live long enough to leave a neat trail. It decays almost immediately into other particles. What physicists actually see
are the decay products, flying off in specific patterns. This is where statistics enters the story. No single collision proves anything. Nature is noisy. Many different processes can produce similar outcomes. To be confident, you must look at millions or billions of events and search for a pattern that appears more often than chance allows. This is a good moment to say something important about science. Discovery is rarely a dramatic moment where someone looks at a screen and it is usually a slow accumulation of evidence. A small excess here, a consistent pattern there, agreement across different methods and detectors. Only when all of that lines up do physicists begin to trust the result. Probability, averages, and distributions do most of the work. Again, calculus is there in the background, helping to describe how outcomes pile up and how small effects emerge from large numbers. But the idea itself is simple. If you flip a coin 10 times, you learn little. If you flip it 1,000,000 times, patterns become clear. When the evidence finally becomes convincing, the particle is not celebrated as an isolated object. It is celebrated as confirmation of a picture in which fields fill space, symmetries guide laws, and mass emerges from interaction, rather than substance. At this point, it is tempting to think, the job is done. The field exists. Its vibration has been seen. Case closed. But that is not how physics works. Every confirmed idea becomes a tool for asking better questions. For example, why does this field have the particular strength it has? If it was slightly different, atoms might not exist. Chemistry might fail. Stars might burn differently, or not at all. Physics does not answer these questions by invoking purpose or design. It simply admits that we do not yet know. This honesty is essential. Good physics is not about claiming final truth. It is about narrowing ignorance in a controlled way. Every explanation has a domain of validity, and beyond that domain lie new mysteries. Another important lesson concerns names. When an idea becomes famous, it often receives a dramatic label. That can be useful for headlines, but it can also distort understanding. A name can suggest importance where there is only function. It can suggest mystery where there is mechanism. In physics, no particle is sacred. Each one is a clue. Some clues turn out to be central, others peripheral, but none deserve reverence. Nature does not arrange itself to impress us. It simply behaves. What makes this field and its vibration interesting is not that they sit at the center of the universe in a philosophical sense. It is that they solve a technical problem cleanly and consistently. They allow particles to have mass without destroying the delicate symmetries that make the theory work. That may sound modest, but in physics, modest solutions are often the most powerful. Nature seems to prefer economy over drama. Let me say something now about understanding itself. Many people believe that to understand physics, you must visualize everything. Tiny balls bouncing around, waves rippling through space. Visualization is helpful, but it is not mandatory. Sometimes the correct picture is not something you can draw. Fields are like that. You can use metaphors, but you should not mistake them for reality. The crowd in the room, the lake surface, the landscape of hills and valleys. These are aids to thought, not literal description. Real understanding comes from knowing what questions you are allowed to ask and what answers make sense. It comes from recognizing which features are essential and which are artifacts of language. One essential feature here is universality. The field fills all of space. You cannot turn it off in one region and keep it on in another. That means every particle everywhere is affected, whether you like it or not. Mass is not optional. Another essential feature is selectivity. Not all particles interact in the same way. Some feel the field strong, others hardly at all. This difference is built into the structure of the theory. It is not explained yet. It is observed and encoded. This selective interaction is part of why the universe is interesting. If everything behaved the same way, there would be little structure. Variety comes from difference in interaction. As you reflect on this, you may notice a pattern. Physics keeps reducing things to relationships, not objects, but interactions, not substances, but processes. The deeper we go, the less sense it makes to ask what something is in isolation. This shift in thinking can be uncomfortable. People like solid foundations, but nature does not promise comfort. It offers consistency. Now let us zoom out for a moment. The field we have been discussing explains only part of what we observe. Most of the mass of ordinary matter comes from other effects, such as the energy stored in the motion and interaction of smaller constituents. Even without this field, protons would still be heavy. The field plays a crucial role, but not an exclusive one. This is another reason not to exaggerate its importance. It is a piece of a larger structure, a necessary piece, but not the whole building. And beyond that building lie unanswered questions. Gravity, for example, does not fit comfortably into the same framework. Neither does the mysterious matter that seems to dominate the mass of the universe, without interacting with light. These problems remain open. If you are looking for a final theory, a neat package, tied with a ribbon, you will be disappointed. Physics does not work that way. It builds scaffolding. Some parts are sturdy, others are provisional. All of it is subject to revision. That is not a failure. It is a strength. It means physics remains alive. So what should you take away from all this? Not the name of a particle, not the details of a detector, but a way of thinking. When you push against the world and feel resistance, remember that this resistance is not a brute fact. It is the outcome of interactions with fields that fill space. When you hear that something exists everywhere, do not imagine a substance, but a condition. When you encounter a mysterious object in physics, ask what problem it solves, and above all, remain comfortable with not knowing everything. Confusion is not the enemy of understanding. It is the beginning of it. Nature is subtle, but not malicious. If you ask clear questions, and listen carefully to the answers, it will tell you how it works. Not all at once, and not without effort, but honestly. That is all one can ask of the universe.